Hey folks, welcome to another set of Chemistry 1 video notes. In our first lesson of Unit 7 today, we're going to be talking about solutions. So you better concentrate. We'll be covering standards C.7.1, C.7.2, and C.7.3, which ask you to describe the composition and properties of solutions, explain how different factors affect the solubility of a solute, and to describe the concentration of solutes in a solution in terms of molarity. You're also asked to use molarity, mass, and volume in calculations and to be able to prepare solutions of given concentrations. So let's get started. Well, first off, what does it mean to dissolve? When a substance gets dissolved, it means that it splits apart into separate particles, molecules, atoms, or ions. We'll see an animation of that here soon. Solutions are mixtures of two or more substances. They're considered homogeneous, which means they have a uniform composition throughout. Unlike heterogeneous mixtures, like sand, where you can see the different pieces, homogeneous mixtures are evenly mixed like sugar water. You can collect a sample of sand and get a different ratio of each of the components each time. But a glass of sugar water will give you the same ratio of sugar to water no matter which part of the glass you collect the sample from. Solutions consist of two components: solvents and solutes. The solvent is the substance that exists in more abundance, or at a higher concentration. You might consider it as a substance that is splitting up the other substance. It's doing the dissolving. The solute is the substance that is present in less abundance, or at a lower concentration. You can think of this as the substance that is being split up, or being dissolved. You've heard the word aqueous before, but here's a clear definition for it. An aqueous solution is one in which the particles are separated and dispersed throughout the solution. So let's look at an animation of how salt and sugar dissolve differently. On the macro scale, you don't see much difference between the solvation of salt or sugar. The only noticeable difference is that the salt causes the light bulb to light up, but the sugar does not. In both cases, we see the solute leave its shaker and hit the water, but then it disappears. What if we zoom in a bit and look at it on the micro scale? Now you can see the actual molecules of salt and sugar that we dump into the water. Do you notice how the chunks of sugar we drop into the water separate into smaller chunks? These smaller chunks don't break up any more than that, though. What about the salt? These large chunks completely separate into individual particles. In fact, they're individual ions. We no longer have any molecules of salt, unlike the sugar. We still have molecules of sugar, they're just separated away from each other. So why do you suppose that is? Let's zoom in a little more and watch this again. Here you can see the water molecules with their partial negative and positive charges. Sugar is a covalent molecule. The partial charges of our water molecules allow them to surround each of the sugar molecules, but doesn't allow them to break them up entirely. When we throw some salt in there, we see those ions get completely split up. Notice how the water's partial negative charges surround the positive sodium ions, and the partial positive charges on the water surround the negative chlorine ions. In both of these instances, our substances are being split apart and surrounded by water molecules. For now, that's the really important part of this animation. Here are 5 common characteristics of solutions. All solutions are homogeneous. The physical state of the solution is generally the same as that of a solvent, so if you dissolve a solid into some water, the solution stays as a liquid like the water was. The solute particles get separated and surrounded by particles of the solvent, much like you just saw in the animation. Our sugar and salt particles got separated and completely surrounded by water molecules. The dissolved solute, if it's truly dissolved, will stay dissolved. It won't separate out from the solvent. And, unlike molecules and compounds, since solutions are mixtures, they do not have a fixed ratio of their components. That is to say, we can change the ratio or the concentration of the components in our solution. There are 3 basic steps to forming solutions. If you remember back to Unit 4, there are some forces that attract molecules to each other. We call these intermolecular forces of attraction. In order for a substance to dissolve, or the molecules of that substance to be split apart, we have to have enough energy to overcome those forces of attraction that are holding them together. Since the particles of the solvent are also attracted to each other, We have to have enough energy to overcome those forces of attraction so they can surround our solute particles. And finally, once we've achieved the first two steps, our solvent particles can be attracted to our solute particles, spreading them out evenly throughout the solution. When this happens, some energy is released. When the energy required to separate particles isn't quite as high as the energy released when the new forces of attraction are formed between solute and solvent, the overall process is considered exothermic and will have a net release of energy. When the opposite is true, when it takes more energy to split up our solute particles and more energy to split up our solvent particles than is released when the solute and solvent buddy up, that process has a net absorption of energy, and we call it endothermic. In our animation from before, both the salt and the sugar were dissolving. On the macro scale, the only noticeable difference was a light bulb lighting up when the salt dissolved. That's because ions have the ability to transfer electricity. The sugar didn't form any ions, but the salt did. When a substance dissolves and forms ions, we call that dissociation or ionization. If our solute creates ions when it dissolves, it's considered an electrolyte. If it doesn't form ions, it's called a non-electrolyte. When our electrolyte completely or almost completely dissociates, in other words, all of the dissolved particles create ions, we consider it a strong electrolyte. And when only a small portion of our dissolved solute forms ions, we consider it a weak electrolyte. The more ions that are present in solution, the more conductive the solution is. That's why the light bulb got brighter as we added more salt. Have you ever made Kool-Aid or tea and just kept adding sugar to your solution to see how much could dissolve? There's a point in which no more sugar will dissolve, and if you add more, you'll be left with a slurry of sugar particles at the bottom of your pitcher. This is the sugar solubility. The solubility of a substance is the maximum amount that can be dissolved given a certain number of conditions. So when we dissolve exactly as much of our solute as we can, the solution is considered saturated. Anything less than that is unsaturated. And if we're smart about it, we can actually trick the solution into dissolving more of the solute than is actually possible. When that happens, the solution is considered supersaturated. There are 5 factors that affect how your solutes will dissolve: temperature, polarity, pressure for gases, molecular size, and stirring. Increasing the temperature increases the particle movement and the energy present, which will increase the solubility. This is the tricky way we get to a supersaturated solution. If we warm up a solvent, our solute will have a higher solubility. We could dissolve more of it than we normally would at room temperature. So if we dissolve the new maximum amount of solute into our solvent, then our solution would have more solute dissolved in it than it would if it were at room temperature. If we let it slowly cool down without disturbing it, we can actually keep our solute in solution while the solubility decreases. That's how we get to a supersaturated solution. Any little disturbance in that supersaturated solution will make our solute settle out or come out of solution. It'll turn back into the solid that it was before we dissolved it. If substances don't have similar polarities, they will not mix together. The common phrase here is like dissolves like. If we stick 2 polar substances or 2 nonpolar substances together, they're likely to form a solution. A nonpolar substance, like oil, and a polar substance, like water, will not form a solution. If you didn't know, gases can be dissolved into liquids. This is how we get oxygen in our water, which the fish breathe in, or how we get CO2 in our carbonated beverages that many of us drink every day. To do this, the solution and gas mixture are put under high pressure. That high pressure causes the gas particles to be more easily dissolved into the solution. And then if we keep it at a high pressure, our gas particles will stay inside of the solution. That's why when you open a container of pop, you hear a hissing sound. That's the pressure being released. And it's also why if you leave that bottle of pop open for a long period of time, it'll become flat, which basically just means the CO2 escaped. If all of those factors are the same, we can look at molecular size as another factor that affects solubility. It doesn't affect solubility nearly as much as the others do, but it does still play a role. Smaller particles are more easily able to be dissolved. Therefore, they have a higher solubility. Finally, our fifth factor is one you already know, but I want to make something clear about it. Our other four factors affect the solubility, or the maximum amount of solute we could actually dissolve in our solution. Stirring does not affect the solubility, but it does speed up the process. So it doesn't change the maximum amount you could dissolve, it just changes the speed at which it does dissolve. You've heard the word concentration thrown around a few times in this video. Concentration is how we describe how much of our solute we have in our solution. There are many ways to represent concentration, such as moles per liter, grams per liter, parts per million or billion, or molar ratios. The most common measure of concentration, and the only one we're going to use in Chemistry 1, is molarity. Molarity is the number of moles of your solute divided by the number of liters of your solution. The units are moles per liter. When you look at molarity, represented by a capital M, that number is telling you how many moles are in 1 liter of your solution. You can and will use that as a conversion factor for some stoichiometry calculations. If you want to create a solution of a particular concentration, but you only have a solid to work with, first start out by finding the molar mass of your solute. Next, using the molarity you're shooting for, determine how many moles of that solute you'll need to add to a certain amount of liters of your solution. Finally, convert the moles of your solute to grams of your solute using stoichiometry and the molar mass. And then at that point, you can measure out the correct number of grams of your solute and then dissolve that into your solution, which is usually water. Now, if you're starting out with a liquid solution of a known concentration, which we generally call a stock solution, then you must first know the concentration of your stock solution. Figure out what volume and at what concentration you want your final solution to be, and then use the dilution equation, which is M1V1 equals M2V2, to determine your volume of the stock solution, which is V1. M stands for molarity here, and V stands for volume. So you plug your stock concentration into M1, your desired concentration into M2, and your desired volume into V2, and then you solve for V1. This tells you how much of your stock solution you need to pull out and add to water until you get to your desired volume of solution. So let's do a couple examples of those on the board. Okay, so the problem tells us 100 grams in 500 milliliters. Our atomic masses for each of our elements are here. If we add those up, we get about 40 grams per mole for our molar mass of NaOH. Next step, take your 100 grams and convert that to moles. Every 1 mole of NaOH is about 40 grams. And if we do that, we get that we have 2.5 moles of NaOH. That's the number of moles of our solute. Then we have to divide by liters of our solvent. We don't know liters though, we know milliliters, so we have to convert that first. 500 milliliters, there's 1,000 milliliters in every 1 liter. So we have 0.5 liters of water. So that'll go here. And if we take 2.5 divided by 5, that tells us that our concentration is 5 moles per liter, or 5 molarity. All right, our next problem says that we start with solid sodium hydroxide, and we want to make a 750 milliliter solution of 6.3 molar sodium hydroxide. All right, so we want to figure out how many moles of NaOH we need to add to our water. To do that, start with your desired volume, so 750 milliliters of water. That's a terrible M there. Convert that to liters, so 1,000 milliliters equals 1 liter. And then convert that to moles based on your desired molarity. So you want 6.3 moles of NaOH for every 1 liter. Now when you're working with solids, the solid doesn't add or subtract from the volume of your liquid. So your volume here can just be the volume of water. If we run that math out, we get that we need 4.725 moles of NaOH. If If you want to know how many grams that is, just convert. Every 1 mole of NaOH equals 40 grams of NaOH. So according to this, we need 189 grams of NaOH in our 750 milliliters of solution. All right, our last problem says that we have a stock solution of 12 molar HCl, and we want to create 1.25 liters of an HCl solution that has a 1.5 molar concentration. So when you're dealing with liquids as your starting point, you need to use your M1V1 equals M2V2 equation, your dilution equation. In this case, M1 is your molarity of the stock solution. M2 is your desired molarity, and V2 is your desired volume. So we'd have 12 molar times V1 equals 1.5 molar times 1.25 liter. Divide by the 12 molar on both sides, and you get that the volume of stock solution you need is 0.15625 liters. Now that's a funny number and probably one that's hard to measure, so maybe if we convert that to milliliters by moving the decimal over 3, we could see it a little bit better. We need 156.25 milliliters of our stock HCl solution, along with the rest of the water we need to get to 1.25 liters to get a concentration of 1.5 molar. Well, that's all for today, folks. I hope you learned something and are now ready to begin mastering these concepts. As always, if you have any questions, please let me know.